Hi. So I broke this thing. Actually, I connected this thing, this watt meter. This was a watt meter actually. So and I connected this thing in reverse polarity and it burned. So I thought of building one myself. So I made this. So this is a normal, this is a watt meter. It just displays volts, amps and watts, and that's all I need. And it's based on Hall effect sensor. It's based on Hall effect sensor and Arduino Nano, and it is powered by 5 volts USB. So we are going to test this thing. So this is the very famous Ruding Tech buck converter power supply. It's outputting 6 volts now, and this is reading 5.99, and we are measuring the voltage which this thing reads here. So this multimeter, and I'm actually comparing the values read by this with this multimeter. So the load is a watt meter, so it's pretty accurate, 5.99, and it is 6. It's really nice. And so we'll increase the voltage and see if we will get the same accuracy. It's 8.99 and it's 9 there and it is 9 here, and we will increase some voltage here and see. It's 9.11 and it shows 9.19. It's okay. And here it is 9.118. So 9.3. Let me reset this thing. Yeah. 9.3. 9.3. So it's not that accurate to fourth or third digit, but it serves the cause. So it can measure up to 100 amps. So now we will give some load. So now 3.1 amps is flowing here. 3.1, 3.2 amps is flowing. That is flowing through this, and the input voltage is 5.23, but it's reading 5 here, and it's 5 here too. That is because this long wire, and there is contact resistance here, and in these two alligator clips there would be some voltage drop. So it takes that voltage drop, and that's why there is 5 volts here. And the input impedance is not so large here. The input impedance of the attenuation is not so high. That is one of the reason maybe. But it is 5 volts there, and it is showing 5 volts here too. So now we will increase the current and power, and we will see. So here it is 73 watts at 11 volts, and it is 10.7 volts here, and 70 watts, 10.7 volts. 10.7 volts. Let's push it to the maximum power, shall we? So 461 amps and it is 476 amps, 27.4 volts, and it is also showing 27 watts. So if you notice that there is zero current flowing through this wattmeter and it shows some current 0.183. So why is that? Why is that? That is because of this. So this is the formula to convert the voltage output from the Hall effect sensor to current. So this particular Hall effect current sensor, that is ACS 758, will give you 2.5 volts, exactly 2.5 volts for 0 amps. But practically that's not the case. It won't be 2.5 volts at all. It will be some voltage. So that is the reason for that offset. So one solution is to measure the output voltage across the Hall effect sensor when there is zero current and feed in the value in the code, feed that value in the code. So then you will get proper reading. But still sometimes these multimeters wouldn't read it precisely, or the values or the offset values would change with temperature, or it might change. It will drift, it will vary. So another solution is to just subtract this offset voltage after all this calculation is done. So that would do. So let us do it and see if it works or not. So after doing some fine-tune calibration and subtracting the offset, so here we are, and it is 0.00 amps. It is tending to 0, and it is zero current there too. It still has little bit of variation and drifting, but that's okay. So let us actually connect some or give some current to the load. So it's 0.98 and it's 0.993. That's awesome. And it is 1.98 and it's 1.993. It's 1.98. It's 1.993. It's 2.99 and 2.983. Pretty close, actually. Pretty close. And 8 amps flowing, 8 point something amps, 14 amps flowing, 14.1, right on it. 325 watts, 320 watts, 17 amps, 17.1. So pretty precise. So thank you for watching.